Hello class. In this video we're going to go over how to solve definite integrals. So what we've been working on the last couple days were indefinite integrals where there is no interval specified across the integral. We're just solving for what function gives me this as a derivative. So here's some basic properties. Now these are not terribly difficult properties to understand, but they are worth writing down because we want to understand how they all interact with each other. I'll actually start with this bottom one because this one we have used already to solve indefinite integrals. And that's when you take the constant and you kind of I like to think of it as factoring it out. Okay. You're factoring out the constant. You can just integrate the function and then multiply by k at the end. Now this one right here says the integral from a to a of f of x dx is equal to 0. Imagine a graph, okay, where you got, I don't know, say something like that. And a to a, well, that's the same number. So that means, if say this is a right here, all you have is a vertical line. You don't have any rectangle for which to calculate an area, and therefore you can't get subrectangles and add them all up. So you just end up with 0. This is one we've used when you're adding two functions, and you can extend this for as many functions as you want. So long as your interval is the same, adding or subtracting two functions, you can split them into their own separate integrals. And we use this more as a mindset, not as an actual practical tool where we take time to write out each individual integral. We're just more thinking through this rather than writing through this. Here's an interesting one. We've got the integral from b to a. Now, typically in this rule, a is considered the smaller value and b is considered the larger value. So it's going from large to small. This could be like, say, 5 to 2, just as an example. Well, then what this is saying is we want it to be 2 to 5. And we can simply flip that interval so long as we take the negative of the area. And of course, we've already talked about how you can have negative area in this unit. Okay, here we've got the integral from a to b and the integral from b to c. Well, what this is doing is it's adding, since it's the same function, and the upper limit on this integral is the same as the lower limit on this integral, you can basically combine these and go from a to c. So, and we could work the other way if we wanted to as well. Take this interval and work the other way. Now, in my experience, you're more likely to work this way, and we'll see examples like that in the future. We won't see any today, but you're more likely to split it up. It's more of a strategic choice. Okay. Now we're going to get to the big thing of this, and this is called the fundamental theorem of calculus. Okay. So this is how you work through the limits. We've worked through a lot where we've worked with definite integrals where they were nice geometric shapes. It was just kind of get us in the mindset of what we're working through when we're working with this integral. But we're gonna see shapes today where we can't use just nice simple geometric formulas. So the fundamental theorem of calculus says that the integral from a to b f of x dx is equal to big F of b minus big F of a. Now, a couple of things. Big F, I just say big F of x, is, if we were to differentiate that, we get little f of x. Okay, so we're just saying that f is the derivative of f, and really I probably should put it this way: f of x, little f of x, is equal to big F prime of x. Okay, so that's what that notation means. But notice we're plugging in our upper, we're plugging in our lower. Now, we just got used to indefinite integrals writing plus c at the end. What happens with the plus c? Well, if we think about it as, and I'll kind of write it over here, big F of b as having some kind of plus c, well, then it would stand to reason that big F of a would also have that same plus c. I want to state this is not proper notation. We shouldn't think through this way, but this is kind of the theory. Plus c is part of the function. Well, you can see they would just simply cancel out. And so because they're constants, they would be the same constant. We don't need to work through what that additional constant would be. Okay, so we just, in the end up anyway with big F of B minus big F of A. And then finally, the average mean value theorem. This is something that comes up where we have the integral from a to b of f of x dx. This would say something like, find the average value over the interval. We're taking the indefinite integral, which would be, again, remember this is just simply area under the curve. Area under the curve. Okay, and then we're dividing by what is effectively the length of the interval. So this is the length of the interval. Okay. All right. So, and let's think about what that word average. We've seen that plenty of times in math classes before. We're taking what is effectively a sum. Remember, this is just a Riemann sum, the limit of a sum. And when we think about average, we think about adding a bunch of numbers together and then dividing by the total amount we have. So this is our sum, whereas the length is considered, and I'll put it in quotes, our total. This would be our list of numbers that we'd add up, and this would be our total. The total being dividing by the difference between the upper limit and the lower limit. And remember that, I mean, it goes without saying, multiplying by 1 over a number is the same as dividing by. So that's why I'm saying it in those terms. Okay, so we're going to look at one problem involving the fundamental theorem of calculus, and we're going to look at one problem involving the average mean value theorem. And they're pretty standard problems. So let's go ahead and talk about solving the integral from 0 to pi of sine x. We actually kind of tackled a similar problem when we were doing kind of more logical integrals and geometric integrals. We had, on that particular problem, I'll say this is 1, and then I'll extend this to be -1. Oh, no. Let me get that. Drew too high initially. I overcommitted. Sorry about that. Okay. Perhaps I undercommitted. Not my best picture, but you got the idea. Okay. We had the integral in that instance was from 0 to 2 pi sine x dx. And it was discussed how we have this area and we have this area. This is the positive area, and because of the symmetry in sine, this is just the opposite of this, which means our total area was 0. Well, now we're not using this anymore. We're just doing solving for this area right here. And as I pointed out, it looks curved like almost like a semicircle, but it's not a semicircle. So this is where the fundamental theorem of calculus comes in. So we think about what is the integral of sine of x. The integral of sine of x would be negative cosine x. Okay. And then how I deal with this interval would just be to draw a vertical line. This is my lower, this is my upper limit. And then we plug it in. So let's plug it in. Let's actually write it out. So we're getting used to seeing it. Negative cosine of pi minus a negative cosine of 0. And this is where your unit circle would come in. So a couple things. We have a minus and negative, that'd be a plus. And from our unit circle, we could see cosine of pi is -1. So that's a -1. Definitely be careful with your negatives. and then plus cosine of 0 is just 1. We have 1 plus 1. So this is positive. This is a positive 1 plus 1. Our final answer. Trust you don't need a calculator for this. 2. Okay. Now, that also can kind of give us a clue as to what this area was. Remember, this area was just the opposite of this area. This area here was -2, but that's more of just kind of a supplemental exercise. That's the fundamental theorem of calculus. All right. Find the average value of f of x on being 4x minus x squared on 0, 3. Does f actually take on this value at some point on the interval? So let's remember that the average of f was equal to 1 over b minus a times the integral from a to b of f of x dx. So let's go ahead and plug in all our information. This is equal to, so our was a and our b was 3. Our 0 was a. Our a is 0. Pardon me. Okay, so we got 1 over, and yeah, we can do 3 minus 0 in our heads, but I'll write it out for starters. We're going from 0 to 3 of 4 minus x squared dx. Okay. So we will simplify this. This is 1/3. Okay. This becomes, so the derivative of 4 is 4x. And then we got to use our reverse power rule. Plus 1, and then divide by that. I always like to write it as 1/3 x cubed. And then our interval from 0 to 3. So 1/3, and then I'm going to use a big bracket because I'm going to plug in 3 for both of these first. It's going to be 4 times 3 minus 1/3 times 3 cubed. And then I'm going to subtract, and I'm going to plug in 0 for both of these. We got 4 times 0 minus 1/3 times 0 cubed. And I'll close my big bracket. All right, so we got 1/3. Now, one thing interesting to observe here is this cancels out. It's just 0 minus 0 is 0, and then we're subtracting 0. We're not changing the value, so let's just focus on calculating this value right here. We got 4 times 3 is 12. That means I can drop the big brackets too. 3 cubed is 27, divided by 3 is 9. So 12 minus 9 is 3, times 1/3 is 1. All right. So let's go ahead and box that. Now, does f actually take on this value at some point? And the answer is yes, because that's how averages work. Averages, or I've always heard described as, you'll have some that are above, some that are below, but when you have a continuous function that continues to flow, it has to hit it at some point. It might elevate through the value, or it might decrease through the value, but it will get there at some point. Okay, let's actually look at what that would look like. Does f actually take on this point? So we'd let me choose a different color. Let's go purple. Actually, no, purple. Let's go with pink. All right. So we have, does f take on that value? So we're just simply setting 4 minus x squared equal to 1. We'll go ahead and subtract 4. And this, you're just calling back to the days of algebra 1. Divide out the negative, you got x squared equals 3. And so then we have x equals root 3. Do we take the plus minus? And the answer is no, we don't. Consider your interval negative root 3 would not fall in this interval, so it would just happen at x equals root 3. Thanks for watching.